Let's take a look at properties of thermoplastics. Because they can reversibly cycle from the melt state to the solid state, let's look at the flow properties as a starting point. We look at a property called viscosity, which is basically a measure of the resistance of a polymer melt to deformation. This can be idealized to the deformation of any fluid. In the schematic over here, look at two plates that are parallel to each other, separated by a distance d. If the top plate is moved by pulling at a force F so that it can attain a velocity v, and we keep the bottom plate stationary, the molecules of the polymer in contact with the plate would move at a velocity v, whereas the molecules of the polymer in contact with the stationary plate would be at a velocity of 0. And so you can imagine that a gradient is set up as a function of distance dv by dy, which defines basically the strain rate experienced by the polymer. If it was a solid, that property is called shear rate in the case of fluids. The proportionality between the shear stress and this velocity gradient is viscosity, referred to by the symbol eta, where tau is the shear stress and gamma dot is the shear rate. Eta is also called the coefficient of viscosity, and its units are Pascal seconds. For Newtonian fluids, viscosity is a constant as a function of shear rate. For non-Newtonian fluids, viscosity is not a constant as a function of shear rate. Let's look at this log-log plot of viscosity as a function of shear rate. At relatively low molecular weights or relatively low shear rates, viscosity tends to be independent of shear rate, and this is referred to as a Newtonian plateau. At intermediate shear rates, you have viscosity reducing as a function of shear rate for many materials that are polymeric, and this is then referred to as a power law dependence. It's linear in a log-log scale. Mainly this is because the alignment of chains improves in the flow direction, and it goes from the disordered state initially. So the greater the shear rate, the greater is the tendency to align, and the lower is the resistance to deformation. At some point, all the molecules are fully aligned at high shear rates, so you end up having a viscosity independence of shear rate at high shear rates as well. What is this cause for resistance to flow or deformation of the polymeric fluid? Consider a polymer chain. In the proximity of many other large molecular weight chains, there are molecular entanglements that constitute a temporary resistance to flow, as schematically shown over here. As the strain rate increases, these chains, which begin to align with the flow direction, cause a reduction in entanglements and hence a reduction in viscosity. You can imagine that higher the molecular weight, higher are the number of entanglements that are possible, and so higher the viscosity. Initially, as you go from a small molecule and increase the molecular weight, viscosity increases slowly with molecular weight. It increases in a linear manner, and at some point there's a transition and the viscosity then goes up more dramatically as a power law. Viscosity scales with molecular weight raised to 3.4 index. This transition point over here is a transition point where entanglements begin to take effect within the polymer. So to summarize, the viscosity dependence is a function of shear rate. For a Newtonian fluid, so low molecular weights or low shear rates, you have a Newtonian behavior. For polymers, especially at intermediate shear rates, you have a pseudoplastic fluid where you have a shear thinning behavior. Viscosity reduces as a function of shear rate. Here is a log plot of viscosity as a function of shear rate for various polymers ranging from nylon, polyethylene, and so on. You can see that intermediate shear rate region, which is different for different polymers, the onset of that region, where you have a shear thinning behavior. Molecular structure, molecular weight, all of them end up defining what this region at low shear rates is and what the nature of the slope over here at intermediate shear rates is. In addition to viscosity depending upon shear rate, it also depends upon temperature. You raise the temperature, the fluidity increases, viscosity reduces. So you can see that from these symbols at 170 to the orange symbols at 200 degrees C. A cross WLF equation is useful for modeling this dependence between shear rate, temperature for viscosity. The viscosity of a polymer depends upon these different factors, which includes the shear rate. N is the power law index. This term eta naught also then captures the temperature dependence based on this WLF portion of the equation. So numerous constants available, but just as viscosity is dependent upon shear rate as well as temperature, as described by the cross WLF equation. We said that we could modify the properties of a polymer by adding fillers. Here is a plot of the relative viscosity, which is the viscosity of the filled polymer relative to the viscosity of the unfilled polymer as a function of the volume fraction of the solid for various particle sizes. What can you see? One is you add fillers, viscosity goes up, processability goes down. The finer the fillers you add, the higher is the increase in viscosity. Guth equation describes this type of a behavior where viscosity increases as the volume fraction of the filler goes up. This part of the equation up to here, 2.5 phi, was developed by Einstein as part of his PhD thesis, which is valid for very dilute solution, and his investigation was in the Brownian motion in fluids. This parameter over here represents the nonlinear portion as you increase particle-particle interactions in the suspension. As you increase the volume fraction beyond these low concentrations over here, you see viscosity dramatically increasing as a function of filler content. And you go from about 10% to all the way to about 50, 60%. In order to capture this nonlinear dependence, the Krieger-Doherty equation, which is shown in its simplified form over here, talks about how the viscosity of the composite depends upon the viscosity of the binder. The ratio of these two will be the relative viscosity. It also depends upon the volume fraction of the powder or the filler, and since all particles have a maximum packing density, the packing characteristics of the filler have to be taken into account as well. If phi p reaches phi n, viscosity becomes infinite as the fluid begins to transition more to a solid-like behavior because of such a large amount of particle-particle interaction.